are only looking at objects that are moving in a straight line. First condition, they have to be moving in a straight line. Second condition, they have to be moving with a constant acceleration. One fixed acceleration. If it is 5 meters per second squared, it must be 5 meters per second squared throughout without any change. Constant acceleration, okay? And you have to know what acceleration means. I made a mistake last week. I noticed it. I was watching the video luckily. Not a mistake. I didn't mention something that I should have mentioned. I missed to say it. So acceleration is a vector, and I said that you would say that something is accelerating if the velocity of that object is changing. The word acceleration is used whenever the velocity of an object is changing. If something is moving at a constant same velocity, zero acceleration, no acceleration. You say that an object is accelerating if the velocity is changing. And I said that, okay, what do you mean by velocity is changing? You could have speeding up, velocity increasing, or velocity decreasing. This is the only two cases I talked about. There is another way in which the velocity can change without a speeding up or a slowing down. How is that possible? Yeah, if you could be moving at the same speed, same value, say okay, for example, since a car is moving at 5 meters per second in this direction, okay? If you keep moving in the same direction at the same speed, this is the speed. Note the word I'm using, this is the speed. Means I'm just talking about the value of how fast you are moving, value, not the direction. Same speed and in the same direction, so this is constant velocity. 2. Because what is velocity? Velocity includes both the value of how fast you are going also and your direction. If both these are the same, you have to listen to understand. Okay? If both these are the same, velocity will be the same. Now here, if this object is moving in the same direction with the same rate with the same speed, 5 meters per second, 5 meters per second, 5 meters per second throughout in the same direction, what can you say about the speed of this object? Constant or increasing or decreasing? What can you say about the speed? I'm only asking about the speed. That means I'm only asking about the value. Constant. What can you say about the velocity? So for speed you said constant. Yeah. What did you check for that? You just checked, is it 5 meters, 5 meters, 5 meters throughout 5 that constant speed? What can you say about the velocity? What do you have to check for that? You have to check both. Is it moving in the same direction? Is it moving in the same speed? If both are the same velocity, constant. If 5 and then 4 and then 3 and then 2 and then 1, what can you say about the speed?
Not constant, changes.
Decreasing. Speed is decreasing. Velocity? Decreasing, changing. Let's just say changing or constant. Just tell me whether it is changing or constant. 5, 3, 2, 1, direction is the same. Speed, changing. Velocity, changing. 5, 6, 7, 8, 9, 10. Speed, increasing. Velocity, changing, increasing. 5, 5, 5, 5, 5, but it's going like that. But everywhere 5, 5, 5, 5, 5, 5. Speed, constant. Velocity, changing. So velocity could change. Just because the size of the speed is the same, you can't just look at that and determine what about the velocity. You have to check the direction as well. For you to say that the velocity is constant, the speed has to be constant, the direction in which you are moving has to be constant to say that the velocity is constant, right? So an acceleration, okay, so when you have 5, 5, 5, 5, 5 in the same direction, any acceleration? Is it 0 or? 0. There is an acceleration. Let me say it again. 5, 5, 5, 5, 5 and in the same direction. Is acceleration 0 or is there an acceleration? 0. 5, 3, 2, 1. Same direction? There is an acceleration. 5, 6, 7, 8, 9, same direction. There is an acceleration. 5, 5, 5, 5, 5, 5, going like that. Acceleration. There is no speeding up or slowing down. Same speed. But the direction is changing, then it is accelerating. Okay? So you should not. So I happened to say last week that if you speed up or slow down, that is acceleration, true. But you might have something that is not speeding up, not slowing down, but just merely changing the direction. Same speed, but changing the direction. Then it would be accelerating. You have to say that it is accelerating because the velocity is changing. Whenever the velocity is changing, you say that it is accelerating. Okay? So I just wanted to correct that. Okay. So make a note. Something. Let's finish this. So that's what I'm saying. So make a note that an acceleration can lead you to something can be accelerating because the speed is maybe going up. Speed is increasing, or maybe the speed is increasing. Or maybe speed is the same, but it's only changing the direction. Then also it's so speed is increasing, speed is decreasing, or changing the direction. Speed might be the same. Changing what am I right? Changing the direction. Acceleration can happen by any of these three happening. This is, I mean this doesn't come under this, okay? This is additional things that we discussed last week. If you want to jot it down somewhere, I don't think we wrote anything like that. Where we wrote acceleration, we will consider acceleration. Whenever, okay, you wrote basic definitions, number 5 definitions was acceleration, we wrote there. Whenever the velocity is changing, we say that the object is accelerating. There you can say there are 3 ways in which velocity can change. And you can add a sentence there. So this is under, did you find that place in your note? This is under acceleration description. You have written whenever the velocity is changing, we say the object is accelerating. Then you add a sentence there. Velocity can change in 3 ways. Velocity can change in 3 ways. By an increase in speed, that means speeding up. That's the normal word you use for it. Speed up, or speeding up, accelerating. If you want, you write speeding up. Or by a decrease in speed. By a decrease in speed. That means you're slowing down. By a decrease in speed. Slow down. The last one, you're neither speeding up nor slowing down. You can be moving at the same speed, but you're changing your direction as you go. Then you're accelerating because you're changing your velocity. Velocity comprises of both the speed and the direction. So if one of those 2 things change, your velocity is changing. That means you're accelerating. So you could be moving at the same speed. So we'll say by a mere change in direction. Change in direction, regardless of whether your speed can be, the speed also might be changing. Then you'll see that you have all the more reason to say that it's accelerating. By a mere change in direction in the motion. Come on. By a mere change in direction. Speed can be, even if the speed is the same, if you change the direction, you are accelerating. So if you are moving in a circle, for example, the example Malik took, that is a lesson, you don't have it, called circular motion. The topic that comes commonly in physics, called circular motion. You study about objects that are moving in a circle at a constant speed. Constant speed, 5 meters per second. If it is 5, but you are going in a circle, that means every moment you are changing the direction, you keep changing the direction, you keep changing the direction. That means you are accelerating. But we are not used to say that something is accelerating if the speed is the same. You don't feel, that's not accelerating, it's constant. No, the direction is changing, then it is accelerating. So, we don't get this scenario.
Next, why do they say in circular motions that
the acceleration is towards the center? Good question. Unfortunately, I can't. We discuss it. Does anyone else have that same question? See, you haven't learned why that is right.
I really didn't get it.
Yeah. Because we have already, it's 8:30. We have only we have 1 hour more for mechanics. Let's finish our lesson. That's extra because we have limited amount of time. Who else is learning that circular motion? You all are doing physics. Okay, so that could be useful to everyone, but we'll discuss that later. I will just tell you what he asked. Think why in circular motion. Now it's clear that why we say that it is accelerating, because the direction is changing. That is clear now. But why do we say that it is accelerating towards the center? That's your question, right? How do we do that? If it is accelerating towards the center, should we not go towards the center? We are not going towards the center. We are circling around it. But then we say that the direction of the acceleration is towards the center. Why is that? It can be nicely explained. If you want a quick response, you know that an acceleration is caused by, Rachel, an acceleration is caused by a resultant force. Nothing can accelerate without a resultant force. We will learn this in mechanics too, when we learn Newton's second law. If you see something accelerating, who's causing it? You can't just accelerate because there has to be a resultant force, a net force. All the time there are many forces acting on us. At any given moment, now right now, how many forces are acting on me? How many? How many you think? Right now, you can exactly say it. 2, 1, 3, 2. You all agree 2?
No.
Right?
1, 2.
How many separate, like the forces that you separate, you can identify? How many forces are acting on me? There are 2. Did you think about 3? There are 2. My weight, the earth is pulling me downwards and the ground is pushing me upwards. These are the 2 forces. And the net force on me is 0. That's why I'm not accelerating. I'm still. That's why I'm still. Because my net force is 0. If there is a net force means resultant force. If there is a net force on me, I would be accelerating towards that force. This is why, let me say that again. If you would accelerate towards the force that is causing the acceleration, right? So in circular motion, your resultant force is towards the center, the centripetal force. That is the net force. You take any object that is performing circular motion, mark all the forces. You know how to find the resultant force by taking the components and Pythagoras or whatever that is needed, and you find the resultant force. You will see that it comes towards the center, and that is the force that keeps it moving in a circle. It's moving in a tangential way, but that force is pulling you towards the center each time a little bit. So you keep turning, you keep turning, you keep turning. You are moving towards the center, but you never you're not directly going into it because you're moving tangentially to it. Like somebody's pulling me that way, but I'm moving this way. So I would be turned. I would be, you get it? Otherwise, without that force, I would be going in a straight line. But because of that force towards that fixed point, you're turning me every time a little bit. I'm trying to move tangentially. Do you get it? But it keeps me pulling, me towards that center. So that's the direction of the resultant force. That means I am accelerating towards it. That's why you're tending to that point all through your motion. That's not the problem. I mean, that is good enough for you now, but it can be even it can be explained even better. Yeah.
This now I'm just thinking out loud.
Yeah.
This now it's just a clear highway.
Yeah.
A clear highway. We are going at constant speed.
Yeah.
Okay. Constant
speed. Okay. In a straight line, that means.
Constant speed. So now there are bends and all.
Yeah. You accelerate.
So let's just
every bend you take. Yeah.
That means acting towards a specific.
That is right. That the radius of your turn. Yes. Whenever you take a turn in a vehicle, if you're not taking a turn, there is a force acting on the vehicle and. There is, yes. Every time you are not moving in a straight line, every time you are taking a turn, that's a little bit of a circular motion. Now, might not be perfectly circular. If you assume that it is a circle, you are performing a small part of a circular motion. Little arc length you are moving. So during that time, there is a resultant force towards the whatever the who produces that force. What is that force? Yeah, you call it centripetal. Which force is that? So what are the forces? This is a different topic we are on, but this is all good. You need to know it anyway. It's a friction. It's a friction. Then you take a turn. Even if you say forget the vehicle. Say you are running and taking a bend. When you are running and when you are taking a bend, think of now. If you are running in a straight line, you would be just doing like that. You would be pushing the ground backwards. So the ground would be pushing you forwards. That's what keeps you going forward. But when you take a bend, you have to push think of how to take a turn. When you're in a bike, you can see it. See how the forces are acting. Can I stop there and think about it? You think about it, okay? So you have to really, if you think that it is you who's moving, then you can feel the forces. You can think, am I pushing something? Am I pulling something? These are your forces.
It's going exactly in the direction.
Okay, so I will stop there, okay? So I will leave you with something to think. So we'll take it up again. Because that's also part of it, but we are still here.
If you are running in a bend, the lighter the bend, the faster the acceleration is.
The sharper the bend. Yeah, the greater the acceleration. Yeah, yes, of course. You do it and it's harder to take a sharp bend. It's easier to take a shallow bend. Okay. So we are going to learn back to the lesson now. So now, what is this now? Motion in a straight line, constant acceleration. This is our lesson, okay? Uniform acceleration in a straight line. So you think of, now I took some examples for actual objects that do move like that. The best example is something that is moving under gravity. If you throw something vertically up, it will be going in a straight line. If you drop something, you don't have to tell it, you go in a straight line, don't go like that. You don't have to tell him, guide him, it will go in a straight line. So that's the best natural example for an object moving in a straight line at a constant acceleration. So if you think of a vehicle or something that is moving in a line with a constant acceleration, we said, if you're thinking of a certain section of the motion, say from A to B, you always have to have a section, like you're talking about from where to where of the motion. This section should be very clear. Now you will see when you try to solve Beal problems, you have to think, for which section of the motion am I applying these equations? You choose a section. You always have a starting point, ending point, a section. It could be the whole motion, start to end, or it could be part of the motion. So that's very important. So that's why I mark A to B, some section. When you have that section, there are 5 different quantities you can talk about related to motion. So if it is accelerating constantly, there is acceleration. Then you would have a starting velocity at the starting point. So you use its initial velocity, symbol is u. And when you pass the final point in one of your section, that's the final velocity. The two will be different. Why? Because it's accelerating and you are in a straight line. The acceleration is due to a change in the speed, not the direction. Direction is constant, right? So these two have to be different. So initial velocity you have, final velocity you have. And then you can talk about how far have you moved, your displacement, and how long did you take, the time travel. Anything else related? Are there anything else? You think, you tell me, think and tell me, can there be anything else related to motion? Can I talk about, what else can I talk about? You try as hard as you can, there is nothing else, that's it. These 5 things, okay? So these equations of motion is a set of equations that connect 4 of these at a time. There are 4 equations that you will learn. Each equation relates 4 of these at a time. So for example, the first 4. And A, U, B, and D, then U, B, T, and S, then A, B, T, and S, like all different combinations. Each equation relates 4 of them. Okay? So these, by applying these equations, you can find the unknown other 2. Right? If each one connects 4, that means if you know 3 of them, you can find the other one. And you can find the 5th one also. If you know 3 out of these, you can find the other 2 by the use of these 4 equations of motion. It's a set of 4 equations. Okay? So I will just give you these. The first one, let's write first. Is this up to where you have written last week? Right. You write a sentence. There is a set of. Yeah, this is exactly where you are. Yes, we are in. We are under this. Yeah, we're doing it up. We just started this last week. Did I start? Okay. What? Yes, take anything. Like you can call it the common pencil case. If anyone needs it, just pass it. You can take anything. Like it's like every gibberish is you name it, I have it. I'm sure I have everything there. Like you say something that you might need in a classroom. Like something. What? Duster? Here's my duster. I bring it from home. Tipex I have. Says I have it. Oh, not a stapler. Not a stapler. I have glue, I have a pair of scissors, I have a sharpener, I have 2 types of Tipex. The good type and the bad type. I can't find the other type. I have highlighter. I have clips. Yeah, clips. You saw the clips. Yeah, clips.
Pencils.
Yeah, clips.
Pencils.
Of course, it's a pencil case. That's the first thing you should have in a pencil case. A pencil. It's called a pencil case. Okay, the sentence is: there is a set of 4 equations. There is a set of 4 equations. Now, when you're writing, when I dictate the note, when I'm dictating the sentence and when you're writing it, you have to pay attention to what you're writing. You have to think of what you're writing and see whether it makes sense to you. The sentence that you're writing makes sense to you. You have to see that. There is a set of 4 equations that relate 4 of these parameters at a time. That relate 4 of these parameters at a time, called in red equations of motion. The whole set is called equations of motion. Called equations of motion. How do you do it in Sinhala, please? You don't do it in Sinhala, you do it in English. Do you speak Sinhala? It's called Chalita Samikara. Chalita Samikara.
Sounds like Sri Lankan name.
Chalita sounds like a name. Yeah, that could be a name of a song. Chalita. Hi, Chalita.
Chalita is
Even Samikara in India. So if you have a daughter, only you can put Chalita. Chalita for the boy and Chalita for the girl. Do a Chalita from here. Okay. Equations of motion, and here they are. Before you, let me first put them on the board, then you copy it, okay? Because the first one of this equation, you already know it. The first one comes out of the definition of acceleration. Remember the acceleration formula? A is equal to, acceleration is change in velocity over time taken. So that is A is equal to V minus U over T. You cross multiply it and rearrange it a bit, you get the first equation of motion. Okay? The first equation of motion is, now you write this set of, there are four. The first one is V equals U plus AT. Okay, write it in 1 by V equals U plus AT. What?
Similar to the equation.
Yeah. This is nothing but the acceleration formula rearranged into like a nicer.
Are we going to learn how to value that?
No. That you should. I like when you said yeah. Otherwise it's like I'm God and I'm giving and here you are. Just take it by faith. I will not show you how it. Just take my word for it. Like there is no. It's nice to see how it happens, right? Where it comes, yeah.
Now I see that you have a question about.
Look, what I said was nothing to do with it. It's just it's nothing religious. It was not a religious comment, okay? What I mean is that in math we tend to do this. We just give you rules, and you have to just apply it. Don't ask why. It's that way because it's that way. That's not a good way of learning. Like when it comes to learning, especially math, you have to know why it happens this way. Why do we do it that way? And why questions have to be there, and you have to know.
The graph.
The graphs also. That's all in this topic. The equations of motion and the motion graphs. That's all. So the one more after this motion graphs. That's it. That's all we have under this. Okay, so that's the first. So which four are connected by this? B, U, A, and T. One is missing. S is missing in that. So every equation connects four of these, and one is missing. Right? Next one. S is equal to UT plus half AT squared. So this connects S, U, A, and T. V is missing in this. Every equation.
Everybody in order like V.
No order. No order. Let's not in order. You can write it.
Order that way. Confused. I also B equations first, S equations last.
If you want to do it that way, fine. Now, do you have water? Do you all have water? Where's your water? You have to bring water. Happy has. Mihir, do you have water? You have. Girls, you have? If you want to drink water, just excuse and drink water, okay? You have to keep yourself hydrated. Yeah, because we are sitting in the piano. How many hours? Okay. Next is V squared. You all know this, right?
Yeah.
Are these new to you? No, right? V squared equals U squared plus 2AS. So it connects B, U, A, and S. It doesn't have T in it. Actually, these three are enough. You can solve any problem just with these three. These three are. This is enough. Redundant. I mean, you don't need the fourth one, but I will give you. The fourth one is S is equal to.
Connects all four.
U plus V
Yeah.
over 2 into T.
Half, it doesn't matter how u plus v or v plus u. How do you remember it? V plus u or u plus v? Do you have a certain v plus u?
V plus U into T.
Over t.
Over T.
Over t.
This is an equation without
Yes.
Without?
Yes.
I'm sure you can make one out of these.
Second equation formed by velocity equation.
Then the fifth equation.
This one.
Formed by velocity equation.
How?
But half the second.
Yeah. Okay, so as I said, actually these first three are enough. You don't have to use that, but that's a complete set. Okay? Then, 4 bullet points, 4 things to remember. First bullet point. After this, you can box these or highlight this. If you need highlighters, there are highlighters. Redundant, enough. This is enough. Okay? Even these 3, they are enough. This is enough. Okay, first bullet point, and this is the most important point, first bullet point. So you put the bullet point and you also say important in red, in block letters.
Is there a short form something important?
Bullet point, there are 4 bullet points under these. Things that you need to remember about this. Not remember, you have to know about this when you want to apply these. Because why I'm giving you as an important bullet point is because after some time you forget what I'm going to say here. You forget. Okay? What it is you can only apply equations of motion if, that is a condition, if you say this is not, if the acceleration is constant, if you have a changing acceleration rate, if the acceleration is also changing, now you know accelerating means velocity is changing. Okay? Now you can apply these only if the object is moving with the constant acceleration. You forget this later. If you see something having the changing acceleration, you can't apply it then. The object has to be moving with the constant acceleration. So let's write that in red. So important in red, and then you, in your normal color, you write these equations can be applied. These equations can be applied to any section of motion of an object, 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 then in red, where the acceleration is constant, where the acceleration is constant. Okay, now I said if you might have an object that in a certain section of the motion, acceleration is changing. But if you can find at least like one section where the acceleration is constant, to that section you can apply this. You just take that section from like P to Q or some, all the rest it's changing acceleration. But for that little part, then you can apply this. Not to the whole motion then. To that section where the acceleration is constant, you can apply. Is that clear? Now you will forget this. That's why I'm emphasizing on it a lot. Second bullet point. Now your normal color. Second bullet point. These equations are in red vector equations in red. These equations are vector equations. Which means, back to normal color, these equations are vector equations, which means they should be applied in a particular direction. Stop. Continue to the same point. Usually we apply them in the direction of motion of the object. Usually we apply them in the direction of motion of the object. Now you will understand all this when we do the first example. Okay? Until that, hold on. Within brackets, positive direction. I will explain what I just said there. Within brackets, positive direction. Now I said these are vector equations. This is the first time I think if you have not learned this in physics, you are coming across this term under mathematics. Vector equations. What does that mean? If you think of maybe I should answer this call.
Yes, I think yes.
Hello. Good morning. Mama put වැඩ කරන්නේ කවුද මේ? ඒ සම්පත් අයියා. සම්පත් මම කතා කරන්නද in time now? 9 plus 1 කතා කරන්නද? මම කෝල් එක දෙන්න. ඔතන තැනේ what option? කියන්නේ? ඔව්. Okay. Yeah, that was a good version. Yeah, it's okay. But it's okay. Yeah, I was saying that I think that this is the first time you are coming across vector equation. What does that even mean? How can an equation be a vector? No, we haven't learned vectors yet. Have you learned vectors? No, you get vectors in P3. Earlier there used to be vectors on the P1, but you don't have it. So with P you haven't learned about vectors. But if you have an idea of what vectors, I think you have an idea of what vectors are. But what do you mean by a vector equation? How can an equation be a vector? Right? What this means is this. What? No. Wait. Now think of an equation like A equals pi r squared. That's an equation, it's a formula to find the area of a circle. These are like just like this. This tell you how to do stuff. Connecting these things. Here you're saying the area of a circle is equal to pi times r times r. This is just an equation, it's not a vector equation. There's nothing vectory about this.
Yes,
Why do we say
it's
it's a vector? Yeah, when you apply this, because these equations contain vector quantities. Velocity is a vector quantity.
Velocity.
This velocity is a vector quantity. Acceleration is a vector quantity. If at least you have one vector quantity in an equation, it's a vector equation. And then these equations have to be applied. You have to say in what direction you are applying them. You can't just apply them. Like when you find the area of a circle, do you say I'm finding the area of a circle in the upward direction? Is there anything like that? No, there is no direction attached to that. But these you have to say I'm applying V equals U plus AT in this direction, to the left, to the right, up, down. Like now this is a straight line motion. So in one direction of that line, you have to say, because in that direction if you're applying it, say, in this direction, that means you're taking that direction to be positive. So if the object is moving in that, if B is in that direction, B would be positive. If it is in the other direction, B would be negative. So you have to take positive, negative into this by considering the direction. That's why they are called B vector equations. Okay, right. Third point, if we know any three quantities, we can find the other two. Third point, Tarindu, if we know any three quantities, we can find the other two. If we know any three, there are 5 things, right? There are 5 things related. If you know 3 things, you can find the other two by the use of these. If you know any 3 quantities, we can find the other two. Last, but another important point, last point is, I did talk about this under the first bullet point, but I'm giving this to you separately. Sometimes, last point, sometimes we may want to apply, sometimes we may want to apply, sometimes we might, okay, we may want to apply these equations to only part of the motion, to only part or section of the motion. Sometimes we may want to apply these equations to only part of the motion of an object. Therefore, it is important to state, underline or highlight the word state. It is important to state, S-T-A-T-E. It is important to state for which part of the motion we are applying these equations. Therefore, it is important to state, you have to say it in your work, to which part of therefore it is important to state for which part of the motion we are applying these equations. It is important to state for which part of the motion we are applying these equations. Within brackets, I'm giving you a tip for this. Use letters to label different parts. Use letters to label different parts. Like you can use A, B, C, D to different parts. And then you can say, I'm applying to A to B, or B to C, or C to D. Use letters to label different parts. Okay, enough theory, let's get into business. Let's see how we can actually use this to an actual scenario, a problem. Here's an example. Example. We are going to, this first example, I'm going to take something that is thrown up. So you're holding it like a certain distance above the ground. You're not throwing it from the ground. You can have questions like that. Things are thrown up from the ground. Like you have to like keep it on the ground and throw it from there. So in this example, you're throwing something up like this. So first it starts from a certain distance above the ground. You're throwing it vertically up. So just think of how it will, what its motion will be. It'll go up, straight line, right? Go up and then stop somewhere and come back down in the same line and until it hits the ground.
Somewhat like a parabola. Somewhat.
How is it about parabola?
Kind of like has the.
If you stretch it like this, no, it's not a parabola. It's a straight line. It's a straight line. If you throw something vertically up, you hold something here and you throw it vertically up, it's going to go on a straight line and come back on the same straight line. That's how it will move. You go up, stop here, and come back until it hits the ground. Straight line motion. That's it. No parabola here. Parabola is when you, therefore, that is if you project or throw something at an angle, not vertically up. This is vertically up.
But there will be like a
No, vertically up. Vertically up means the angle between the vertical and your direction of throw is 0. No angle. If there is an angle, if you throw something, who can catch nicely? Watch how this, watch the path of this. Now, if I can't now, maybe this is what you are trying to point out. It's very difficult to throw something up vertically. Like you might be thinking, do I measure it vertically? Means 90 degrees, right? Like this.
Yeah.
You can't practically, you might not be able to practically do it.
Yeah.
But I'm talking about throwing something up vertically. Then it will move in a straight line. But if there is any slight angle, then it's a parabola. That's that what you're saying? If you throw something at an angle, can catch?
yes.
That's a parabola. Did you follow the path? That's a parabola. Can you throw it back to me? I'll try to catch it. If you put a nice throw. That path it followed, it's a parabola. It's the function that it's the graph of a quadratic function. Isn't that amazing? It's the same shape, like that shape. It's exactly that. How does it know to go along a parabola?
Then next.
Did it learn math? Yeah.
It's like
This is how nature. This is what we've learned is connected to nature. It follows the path of a parabola. It's amazing. If you think about it, exactly a parabola in the absence of air resistance that has to be added. Right. Okay. So this first example, we are going to take something like that. So let's write. Let's consider.
This field in that
Under the example, you are not in this world. You lose bits of parts in the what I'm saying, I think. Are you writing? He's another one. You, for a few seconds, you go somewhere, comes like looks up and down. Let's consider an object. Held 8 meters above the ground. Also, you are doing local advanced level. You are doing both. You are doing local advanced level. This is in October. And then you are doing after. You are not doing this time. Like this October? No. Because there is a webinar series, but it's happening in Sinhala. Like it's done by the Ministry of Education. It's a revision webinar series for combined maths. There was one webinar last night. There is one happening Monday. And I'm doing it on the Monday one. But it's in Sinhala.
Is it one of those things in Gaya?
That was also put together. That was by 90. No, I don't.
I only got the diagrams. I think we can think.
Okay, you can listen to it if that helps you. But that will be in single. So we are going to discuss some past paper questions in combined maths. Huh? You have to register for it. Yeah, I'll send you the link if you're interested. You have to register and then you can come on 7 to 9 on Monday. Okay? In Sinhala. Right, okay? So let's consider an object. Let's 8 meters above the ground that is thrown vertically upwards. That information is important. It's thrown how? It's thrown vertically upwards. It's thrown vertically upwards at a speed of, I'm giving you the initial speed of throw, at a speed of 50 meters per second. Let's consider an object held 8 meters above the ground that is thrown vertically upwards at a speed of 50 meters per second. Right? Like that. We'll stop. The object finally reaches the ground. The object finally reaches the ground. Upwards at a speed of 50 meters per second. The object finally reaches the ground. This type of motion is called, this is an example, but I'm giving you some extra things. This type of motion is called, write in red, motion under gravity. Motion under gravity. Because it's moving freely under gravity, under the influence of gravity. It's called motion under gravity. Good start, yes. Next slide. The object will accelerate. The object will accelerate with, in red, gravitational acceleration. Gravitational acceleration. In brackets, let's write down the value of that. It's approximately, the symbol we use for gravitational acceleration is simple G. And it's approximate, it's exactly 9.8 something. We take it to be 10. 10 meters per second squared. The object will accelerate with gravitational acceleration. Within brackets, you give the value, close the bracket, in a straight line. The object will accelerate with gravitational acceleration in a straight line. Okay, can you do a little sketch? So here's the ground, here's the object. It's 8 meters above the ground. If you start chatting, this will not be going into your heads. No other conversations during the class. If you are talking about the problem, that's fine. Anything else, not allowed. Okay? If you want to take the best out of this, no chatting. Anyway, there should be not any chatting. Okay? So you say throwing from there, so you go up. So it actually happens in a straight line, but I will just show it like that because otherwise I can't show it coming back. Okay? So I'm going to show it, you go up, it's going to come back along the same line, but I will show you like it's turning like that. That's not how it happens. It turns back and comes along down. No, that's not how it happens. Now please remember, okay, even though we would all draw like that, but that's not. Does it like go to a side, go sideways at the top there? No, it just stops and just drops back down. So it comes back along the same line, but since then you won't see anything. You can't like differentiate between the going up and coming down motion. We'll like do a small curve there and show it separately. But so remember, there is no such thing happening there, right? And then this comes back down. So that's the motion.
This in mechanics, we assume G to be 10 meters. 10 meters per second square, not 9.8.
inconvenience?
When it is fall, like the atmosphere,
Yeah.
then it doesn't continue to accelerate, it stops accelerating at some certain.
That is with air resistance, yes. Like it doesn't happen near the ground, it happens like, if you have time to fall through the atmosphere for a long time, what happens is, as you speed up, you're accelerating, you're gaining speed. As you gain speed, your air resistance increases. Because air resistance is something that the faster you go, you feel this, right? If you're walking, you don't feel any air resistance. Start running, you feel the rush of air through you. So as it accelerates, as it speeds up, the air resistance increases. So there can come a point where the acceleration exactly balances your weight. So resultant force becomes zero. And you would start moving at a constant speed at that point onwards.
You
That's
feel like floating then?
Not, you are moving down with a constant speed.
Yeah, no, like.
Not floating. You would imagine you just stop falling.
No, not like that.
Oh, you're just there floating at point.
I'm talking about the sensation, like the feeling.
The sensation. The sensation would be bearable. But have you ever gone in a roller coaster? Like, have you ridden?
Yeah.
Not really.
When you accelerate, when you fall under, how many of you have experienced that?
Really?
It's a difficult feeling in your stomach. Yeah, my God.
Never noticed that.
If when you like, even when you go in a lift, that is a little bit of an acceleration as it starts, you feel something in your stomach. So imagine that happening like 50 times more. That's what you feel in a roller coaster. But like as you said, what you're saying is, Nandit, if you are moving at a constant speed, you don't feel that uncomfortability in your body. Like when you're accelerating, you feel your organs like, you feel vomitation and all that.
That's
Yeah,
right.
that's not good.
When we fall, like
When you fall, yeah.
then you don't feel as if you are falling, right?
When you fall, you feel.
When you come to that level where
You feel that you are falling, but it's not the feeling is not uncomfortable. When you accelerate, that feeling is uncomfortable. I don't know whether you get what I'm saying.
Yeah.
If you are falling at a constant speed, your body won't feel anything unusual. Like it's like staying at rest. But when you accelerate, the feeling is different.
I should get that in my bucket.
Yeah, in the swing you feel it, like if you swing very high, when you come down like from the top, you feel something in the swing. Yeah. Don't go on
I should put that in my bucket list all the time.
do bungee jumping.
And then I should remember what you said.
Okay, let's start. Did you copy this? And you're starting from 8 meters. So this is 8 meters. Up to that level, this is 8 meters, right? You're throwing it up from 8 meters above the ground. So you draw that. You can show like this is going up and then coming down. What's that?
should be fine.
Let me answer. So you draw that and then say. Now let me ask you. I'll first finish copying this.
How is the initial speed?
Right? Now, so I just gave you a scenario, right? I said you are holding something 8 meters above the ground and you're throwing it at 50 meters per second. That's all I've given you, 2 information. Looks like I've given you 2 information only. Let's just talk about what things do you think we would be able to find about this motion? For example, let me start. I will start with one. Then you tell me. Okay? For example, might we be able to find after how many, from the time I throw it, after how many seconds it will hit the ground? Can I find that?
Yeah.
That's one question. What other questions come to your mind about this motion?
That I have taken to reach the max.
The time taken to reach the top. Can we find it?
Yeah.
What else?
The velocity is like so.
The velocity of it as it strikes the ground. Just with what velocity it hits the ground. Another question. What else can we ask?
Height. It goes.
How? Did you ask that? Did you say that? No. The height it reaches, the maximum height it reaches.
The
Okay.
total
The
distance.
total distance traveled. What
The
else?
displacement.
The displacement. That I can already answer. What's the total distance? Displacement? 8. Starting point, ending point, that's 8. Remember what displacement is? You don't need equations of motion. But that's a question that you can ask. What are the questions? I'm getting you to like form the. Did we ask all the possible questions that we can ask about this? But what did we say?
What would be
How long would it take to finally reach the ground? How long would it take to reach the top? How far? What's the maximum height? That is this distance. How much is that? What else? Distance, total distance traveled. Then how long does it take to reach the top? Just to reach the top.
At what point does it reach the middle, at the point where the ball is thrown and
Like
starting point.
here? How long does it take to reach back the starting point? Like that means how long would it take to come back to this?
what speed?
At what speed would it be passing that point when it's going back down? So many things you can ask.
What is the point of speed before it reaches the ground?
What is
Before it makes contact with the ground, what is the
speed? Yeah, that too we said that. With what speed would it hit the ground? Right? Do you think we can answer all these questions with just these two information? Do you think we can?
Yes.
All you have to ask is, I said, if you have 3 information, that's all you need. You can find all rest and all other things about that motion. You need 3 things.
We have 3.
Where's the third one? What's the third one? G. I don't have to read to it. If it's moving under gravity, you know the acceleration of this object is 10.
Minus 10.
We'll see whether it is plus 10 or minus 10 or all that. Okay, so we do have 3. So you can, to any question that you ask, we can get answers using the equations of motion. Okay, so I will give you not all the questions you asked, but I'll give you some. So after you do this, right, let's see whether we can answer the following questions. Let's see whether we can answer the following questions. Let's see whether we can answer the following questions.
This is really impulse calculation.
Part A, impulse is spontaneous service.
It's like further.
You have momentum from the newly introduced, but no impulse. So impulse is change in momentum. Energy goes on power we have.
Which part is it?
Part A, the distance.
Let's see whether
What? Did you just wake up from a nap? Let's see whether we can answer the following questions.
Yes.
Part A is
Finding the ratio.
right. Part A, the distance traveled to the maximum height point or maximum highest point. No, we say distance travel. Can you fix that?
Yeah.
The distance traveled to the highest point. Part B. You can add your own. I will give you 4 if you like. Add more this. Okay. Part B. The time taken to reach the maximum point or the highest point. Highest point. Yeah. The time taken to reach the highest point. The time taken to reach the highest point. Part C. The total distance traveled when reaching the ground. The total distance traveled when reaching the ground. Part D. The speed with which it hits the ground. The speed with which it hits the ground. Now, before we dive into this and start to find this motion, let me tell you this. Any motion under gravity is a symmetrical motion. The motion is symmetric. That means I throw this at 50. When it comes back and passes the same point, it has to go down, passing that point at 50. The going up motion and coming back down, it's symmetrical. Like now, I will take at 50. So you're throwing it up at 50, right? After 1 second exactly, if gravitational acceleration is 10, after 1 second, what would its speed be? Huh? 10? Huh?
40.
40. Wait. Okay. What's the motion what happens to the speed as it goes up?
Decreases.
It decelerates. It's negative acceleration. 10. Same value is 10. It slows down 10 every second, by 10 every second. The acceleration is 10 meters per second squared, means every second the speed either would increase or decrease by 10. When you go up, you are decelerating. When you come back down, you actually gain speed. When you go up, you lose speed. How do you, at what rate do you lose speed? Every second you lose 10. You lose 10, you lose 10, you lose 10, that means eventually you will be 0. And then from that point onwards, you start falling down, and every second you will gain 10 every second. You get it? So 50, after 1 second 40, after 1 second 30, after 1 second 20, after 1 second 10, after 1 second 0, starts falling back down, after 1 second, another 1 second 10, after 1 second 20, 30, 40, so 50, 40, 30, 20, 10, 0, 10, 20, 30, 40, 50. At the time it passes back to that same point. Symmetric. 50, 60, 70, I don't know how far to go, how much to go. Every second, but in going up, you lose 10 every second. Coming down, you gain 10 every second. That's the meaning of gravitational acceleration is 10. That's the meaning of that. Okay? So, now, let's try each part individually. Now the first part, the distance traveled to the maximum. So I want to find this distance or this displacement s. That means I have to apply equations of motion to, what do you see? The whole motion is this. But in order for me to find the distance traveled from here to here, I have to only consider that section and apply equations of motion to that section. So let's label. Now I'm doing this question very slowly. This is like absurd that I'm using this one. But I'm doing. Not that, buddy. The one I'm writing on the book. He's showing me. Yeah. Thank you. Yeah. Blue mark pen. Yeah. Sorry, I actually did this. Let's label this as A, and that the highest point as B, and then maybe here C. So if you want, you can consider A to B motion, or B to C motion, or the full motion A to C at once. And these are different options you have depending on what they are asking. Now, since in part A they are asking the distance traveled up to the highest point, I have to apply equations from A to B. So that's my section, A to B. So initial speed, final speed, whatever the acceleration, displacement, the time taken. Those are the 5 things that are related to that part. You understand? Okay? Okay. Now, so we are doing part A. Part A. You have to state, remember I said state to which part of the motion you are going to apply equations of motion here. Now part A, they are asking the distance at the maximum point. So from here to here, the maximum height. So I am applying from, you have to say A to B. You have to state it, yes.
Instead of stating it that way,
Yeah.
can we just
In any way you
show
want.
the direction which it's going to take? Like we draw an arrow after saying.
No, the arrow has to be drawn anyway. Now, when you are applying your equation of motion, you have to say in what direction you are applying it. That doesn't say which part of the motion you are considering. It's just telling you the direction.
Can we just write S under A? Like, write S and then below S to the right side, we can small.
Like that?
Yeah.
Yeah, you can do that, but even still, that doesn't explain that you are applying the equation to that section. This means displacement from A to B. Whenever you are applying an equation out from the equations of motion, you have to say from where to where you are applying it. I'll tell you why. Without that, when you say initial speed, final speed, where is your final speed? How do you know? Like, if I don't say this, okay? You write what you know. You say you may be 50. You say V. V where? Is it V here or is it V all the way there? Or is it V somewhere in between? Who knows which part you're talking about? So this U and V defines a certain section. Initial, final. When you say it defines a certain part of your motion, and you have to say what part that is you're talking about. So from A to B, you have to say, and let's quickly do this first part from A to B. Okay, and the second thing you say that's the first thing. Second thing, you write a list of what you know. For that motion, there are 5 things. Out of the 5 things, what do I know about the motion from A to B? Do I know U? Do I know V? Go through the list and write everything that you know. So, U. Here itself, and we will show the direction. We are applying it that way. Because it's going, usually we apply the equation of motion in the direction of travel. It's moving up, we are going to apply it in that way. That means you are considering that direction as positive. Upward, positive. Okay? If something is happening this way, it has to be negative then, but that we don't have to worry about that. We are just considering up to point B, and in the upward direction. What's U? Do we know U? For the AB section, do we know U? U means initial speed at A. Do we know that?
Yeah.
Rachel, you're thinking so. Do we know that? What is it? For the motion from A to B, for this motion, do we know the initial speed? We don't know. We don't know the speed at A. Initial speed, our section is A to B. Let me draw it this way. There is a point A, there is a point B. Do we not know the speed of this object at A? We do. How much? 50. We know it. Is it hard to figure out? Here I have shown it here. You're throwing it at 50, that's the initial speed. So U is 50. Do we say plus 50 or minus 50?
Plus 50.
Plus 50 because we are applying it in that direction. That is my positive direction. So plus 50 is going up. Plus 50. No need to write units. Yeah.
Let's just say we state that we don't have the Southern equation, but at the end of the equation, 3 words, say from A to B.
That doesn't make sense. When you apply, you have to figure out to what section you are applying it. How can you say it in the end? That's the first thing you think. Now, you can't apply an equation without knowing to which part you are applying it. That doesn't make sense. It's like you start going somewhere, you don't know where you're going. And you go there and you say, this is where I have come. Right? Before you go, you have to know where am I headed to. It's like that. You have to know this beforehand. What else we know? What are the 5 things? U, V, A, T, S. We know A. Is it plus 10 or minus 10?
Minus.
Where does the minus come from? Why minus?
Because
it's decelerating at 10. It's 10, true, but it's decelerating at, it's a negative acceleration. It's a retardation, it's negative 10.
Which means if the arrow is downward, it's
It will positive 10. That's correct. Good. What else we know? We need part 3.
S.
Do we know S?
No.
Do we know? Now, what are we trying to want? Let me start. Wait. Let me start with what we want. What do we want?
Yes.
S. S is what we want. S question mark. Now we need 3 more. What we want more?
Please.
V.
We know V. Final velocity.
0.
Why is it 0? It stops and comes back down. At the topmost point, the velocity for a momentarily at that point it's 0. So the final velocity for that section right here it's 0. Now you have 3, you can find S. You look at this and look at your set of equations and decide which one you should use. The one containing S, U, A and B. The one containing S is what we want to find, U, A and B are what we have. So which equation has these 4? V squared equals U squared plus 2AX. Do it. 0 is equal to 50 squared minus 2 times 10 times S. So let me straight away write S is equal to how much? 100 divided by 20? No, 50 squared, that is 2,500 divided by 20. How much? 125. In the answer, you put the unit meters. Now this S equals question mark can come, like I usually write it and here. What I want, what I know, what I want. 3 you have to know, then you can find anything that what is left out. So they are asking for S, there you have your S. Now the thing is we have to stop.